Welcome to the first Bhaumik lecture of 2018. I'm delighted to have Sir Roger Penrose give the first lecture of the year. He's, of course, very famous in physics and mathematics for many of his ideas. And that includes ideas of the cosmic censorship idea, twistor theory, Penrose tiling, which then led to quasi-crystals, and he has interesting and bold ideas for understanding consciousness and the early universe. We'll hear a little bit about his work on the early universe today. He's won numerous prizes. That includes the Wolf Prize, Eddington Medal, Royal Society Medal, Albert Einstein Medal, and of course, knighted by Queen Elizabeth herself. And he served as president of the International Society on General Relativity and Gravitation. And as I'm sure most of you know or own the books, he has numerous very successful books on ideas in physics and mathematics. And today he's going to tell us about dark matter decay according to conformal cyclic cosmology. Without further ado, I give you Sir Roger Penrose.
Well, thank you very much for that introduction. It's certainly a great honor for me to come here and speak and give the first Manny Bhaumik talk of the year. And he's here too, so it's a great pleasure for me to pay my respects to him in person. Anyway, as you see the title up there, it has to do, well, CCC, as we've had explained, has to do with cosmology. It stands for conformal cyclic cosmology, which is an idea which I've been trying to promote for over a decade now, with a lot of opposition from the community, I guess, of conventional cosmologists. I do want to say, though, just a week ago, there was a paper published. I'll start my talk by giving a reference to it, because it's the first time I think that a major, we had stuff published by the Royal Society before, but not the Royal Astronomical Society, and these are the monthly notices. And I think having this paper out, they give, the authors of this paper give a very clear and thorough examination of the Planck data of the cosmic microwave background, and have searched for a particular signal which this theory predicts should be there, and they find that it is there with a confidence that its probability of being correct is 125 to 1. So despite the fairly large number confidence that it might be correct, they were, the referees, they had a lot of trouble getting the referees to accept it, and there are a lot of complaints made, and they dealt with all these things very religiously. And finally, the journal had to say, well, I'm afraid we'll have to accept your paper. They didn't put it quite like that. But they did say that they would have to, on condition that in the opening part of the paper, the authors said, well, it may be a chance effect. But you've heard what the probability is that it's a chance effect, so maybe it's serious. Anyway, let me talk about the scheme, first of all. And before talking about it specifically, let me give you a picture of the universe. Now, I have to remember to get these things the right way up here. So this is the universe more or less according to me, as well as the conventional, what's called the lambda CDM model. And this shows the history of the universe. The universe, of course, in space and time is four-dimensional, and time goes up the picture, and you have to think of time as sort of sections of this thing as it goes up. This, of course, should be three-dimensional, and the surface, well, it should only be four-dimensional to get a surface in it, which is three-dimensional. So you have to imagine pushing the dimensions up where necessary. You may wonder about what all this frilly stuff is at the back. That's just because I don't mind, from the point of view of theory, whether the universe is actually closed up at the back, so the pictures will make it look as though it's meant to be, but it doesn't have to be. It could keep on going. It could be open or it could be closed, and both possibilities fit in with what I want to talk about. Now, those of you who know about these things, and I guess those of you who heard the talk by Paul Steinhardt, which I guess was given last week, was that right? Think that conventional theories say that there should be something else in this picture, which is what is known as inflation. But I might say maybe it is already drawn in the picture because it would be tucked up into that little black point at the bottom. And from the point of view of the scale of the picture, which is pretty well to scale, from the point of view of the scale of the picture, you wouldn't know whether inflation is there or not. There's another reason I haven't put it in the picture, and that is, like Paul, I don't actually believe it. However, let me, to give you some indication of what inflation is supposed to look like, let me bring out a powerful microscope or magnifying glass so you can have a look at it. And what you see, according to inflation theory, is this. Now, I should explain that this top part of the picture is the handle of the magnifying glass. It's nothing to do with the universe, but the universe is supposed to have undergone this exponential expansion, which is very similar to the exponential expansion that we do observe in the actual universe. I should say a little bit about that before going back to inflation. You see, Einstein's equations, as originally presented, predict a sort of expansion like this. So it's rapid to begin with and starts slowing down. But if there is this term that Einstein introduced, the theory as a whole was introduced in 1915. In 1917, he made a modification where he introduced this thing called the cosmological constant, which is usually represented by a lambda, that's thing here. Now, he introduced the theory, the lambda term, the cosmological constant, for the wrong reason. He wanted to have a static universe, which didn't change with time overall, and but it became clear that the universe was actually expanding. Hubble and others showed this, that Einstein regarded that it is his greatest mistake to introduce this cosmological constant because it prevented him from predicting that the universe was actually expanding. But you see, you can also have the expansion with the cosmological term, and even if it was Einstein's greatest mistake, it would turn out to be true after all anyway. So if you're Einstein, your mistakes can still be perfectly correct. Now, let me say something less conventional. One has to do with the inflation, but I'll come to that in a minute. Like Paul, I don't think it's there, but if it's not there, you have to make sure there's something there that does the good things, inflation. It does some good things and it does some bad things, and the good things you want to have another reason for, another explanation for. But let me say what I want to do here. This picture of the universe, like all pictures of the universe, has a problem that it's infinite. Well, all pictures of the universe as we believe it currently with this exponential expansion here. So it's nice if you could make it look finite. So I'm going to do two little tricks. These are mathematical tricks. I'm going to squash down infinity and stretch out the Big Bang. I better have a smaller universe, the same universe but drawn smaller, I should say, to do that. So here we have two tricks. The squashing down of infinity to make it a finite boundary, and the stretching out of the Big Bang to make it another finite boundary. Now these two tricks, well, let me first talk about the one's infinity, because it's something that many of you may have seen a version of this sort of thing. Here we have a well-known Escher picture representing a particular type of geometry. It's called hyperbolic geometry. Don't worry too much about that. But the point is that this picture represents the infinity of this universe, which these fish creatures inhabit, and their infinity is this finite boundary. Now, the other point about this picture, not just that infinity is represented as a finite boundary, but that it's conformal. Now, conformal means that if you can squash the picture down somewhere, but you've got to squash in all directions by the same amount. So if you squash horizontally, the vertical squashing must be by the same amount. And this means that angles are preserved, even if the size is not. And circles in particular, you see the eyes of these fish are all circles, and they remain exact circles right up to the edge. So the conformal squashing and stretching preserves small shapes, but it does not preserve the size of these shapes. Now, when you have a space-time geometry, it's a little bit different because space and time are not really quite the same as each other, as you may well have noticed. And we have these things called light cones, which separate what are called the time directions from the spacelight ones. So this is a point in space-time, and this cone represents what light does. And in fact, here I have a picture with the clocks as well. You see, I want to say, in Einstein's theory, you have to have a thing called the metric, and the metric is usually represented by a letter G, and this G is actually a tensor, but this gives you a little bit of structure, and the structure in these space-time pictures is given by these little cones. Of course, you have to imagine there's an extra dimension from these pictures, but you can get used to that idea. See, the light cone represents a flash of light here. It can be a conceptual flash of light. I'm not saying there's actual light there. A conceptual flash of light, and this speeds out, goes out with the speed of light, and the history of that flash is this cone. So it starts with and you have a pass cone too, which you imagine the flash of light coming in. These things, which may look like circular sections, are actually spheres because of the extra dimensions. Now, that's the conformal structure. That's the kind of information that is preserved when you squash infinity down or stretch out the Big Bang. They're conformal in that sense. Now, a physical statement to make here is that Einstein's metric quantity requires 10 numbers per point. So there's a little 10 here, which is the number of components that the metric has. So you need these 10 numbers to tell you what the metric is doing at any point. Now, 9 of those numbers, or it's not quite 9 of them, but the ratios of those 10 numbers, so 9 independent numbers, are what define the cone. So it's 9 out of 10. So if you like, it's most of the information, in a sense. So the information of the light cones, or the null cones, I should perhaps say, is given by these 9 ratios. So in a certain sense, that's most of the geometry. The extra little bit is what clocks do. You see here I have imagined the history of various clocks zipping along at different speeds, and the first tick of each of these clocks represented by this bowl-shaped surface, the second tick, the third tick, and all that. They're supposed to be identical clocks, but going at different speeds. The tick rates are affected by relativity, and so you can describe it by a picture like this. And these are the clocks coming in from the past, so you have these cones here. So the 10th number, if you like, is the crowding of these surfaces. Now, one thing about physics, and which is so important for general relativity, is that clocks are extremely precise. That we now have clocks which are so accurate that one of the effects of Einstein's theory, for instance, is that clocks are at different rates depending on their heights. And people usually talk in heights of many meters, but nowadays you could have a clock at this height and go a little bit up above it, and you can measure the difference between the time right here and here. So there's extraordinary precision in this measurement of clocks. And once you have the time, then since conformal means that you scale one way and the other way equivalent to each other, you also have distances very precisely defined. It used to be that the meter rule in Paris was the definition of the meter. The meter is now completely differently defined. There's a definition of the unit of time, which is a bit complicated, but the distance is then defined in terms of how far a photon can get in a second, so that the light second, if you like. So the meter rule is now not what one would use. It's not nearly precise enough. But you see that it's the clocks which determine the geometry together with the light cones. Light cones and clocks give you everything. Now, the reason, in a sort of deep sense, of why clocks are so precise is that it comes really from the two most important equations of 20th century physics. One of those, of course, has to be Einstein's E equals mc squared. The other is E equals h nu, Max Planck's equation, basis of quantum mechanics. Now, E equals mc squared tells you that energy and mass are equivalent. There's just this constant, which is the speed of light. Energy and mass are equivalent. Planck's formula tells you that energy and frequency are equivalent. That's Planck's constant now, is the ratio. Put the two together, and that tells you that mass and frequency are equivalent. So if you have a stable particle, a particle with a well-defined mass, that particle is an extraordinarily precise clock. You can't quite use it as a clock because the frequency of that clock is extraordinarily high. So you have to have some way of getting it down to something you can make use of. But the point is that it's inbuilt that mass gives you rate of time automatically. So that's an important thing I want to say. But the opposite of that is if you don't have mass, suppose you only had particles which don't have any mass running around, say photons, that's the particle of light, then it zips along the light cone, it never hits any of these cones here, it doesn't experience any time at all. If you only had massless particles, you would not have any measure of time. That's an important thing to bear in mind. So if you like, although this is the relativity context rather than Escher's, these fish, if they have a mass, which I suppose they're meant to here because they actually get smaller towards the edge, but if you had things which didn't have a mass, then the boundary here would be like anywhere else. And that's the point I want to make. So you can say infinity, as in the Escher picture, is just like anywhere else. And, well, it's just not quite like anywhere else because it's where infinity comes, and it comes to an end, if you like, there. But it comes to an end at a finite place. But you could imagine photons zipping along, and when they get to infinity, they don't know that anything special has happened. So that's the right way to think about it. Okay, and in fact, there are general theorems. There's a theorem due to Helmut Friedrich. Oh, that's the next slide. I should get there now. In fact, I was saying this in slightly different order here, but let me get back to that. There's a theorem due to Helmut Friedrich, which says that if you have even variant perturbations to this model, you see these are, initially you think of the standard classical cosmologies, which are completely uniform and no irregularities, and then you can certainly do both of these tricks. But if you have irregularities, and if you only have massless material, say photons running around, then this future boundary still exists. It's a completely generic thing. So there's a logical difference between these two constructions. One is the future is a perfectly thing you could expect to be able to do for one of these exponentially expanding universes. I should say the presence of this cosmological constant, the exponential expansion, is crucial for this infinity to be what's called space-like. So you can imagine it cutting right across the universe in this way. Now, what about the Big Bang? It's completely the other way around. Most models of possible cosmological models would have a Big Bang which is completely different from this. This is a huge, huge restriction. I'll come to this again shortly because it's very important to what I want to say. But before getting to that, because first of all, there's nothing particularly unconventional in what I've said here. This is perfectly good standard cosmology that my cosmological friends wouldn't, I think, complain too much about, apart from the inflation. They wouldn't like that probably. But what is outrageous is this. I am supposing that imagine that this is I'm going to call it our eon. That is what we currently, in current cosmology, is regarded as the whole history of the universe. But I'm saying that this remote future, thought of as a conformal space with its boundary, becomes the Big Bang of another eon. And our Big Bang was the future development of the infinity of the previous eon. So there's a succession of eons, which I'm saying may be continued indefinitely in both directions. You might have a theory in which it didn't be indefinite, but I'm supposing it's indefinite in both directions, where the matching of each infinity is completely conformally smooth to the Big Bang of the next one. Now, why am I saying this sort of thing? Well, let me go back and talk about the infinity, first of all. What do we really expect to be lying around in the remote future? Well, there'll be lots and lots of photons around. That's as far as particles are concerned, that will be the major thing. But the other thing that you expect to be around are black holes. Now, black holes, according to Stephen Hawking, are not entirely black and not entirely cold. However, the temperature of even the hottest of the black holes around, you have to think in terms of the coldest sort of temperatures that can be made in the lab. It's really very, very cold. And the universe background radiation is a lot warmer than that. However, as the universe expands, then even the hottest and smallest of black holes around will become the hottest, well, they'll become the hottest things around, but the coldest ones will be the supermassive black holes we have in our Milky Way galaxy, a black hole which has about 4 million times the mass of the sun. There are a lot bigger ones around too elsewhere. That has extremely cold temperature, so you have to wait for the universe to expand and expand and expand and get colder and colder and colder. And then eventually it will be the hottest thing around, and it starts to radiate away. It's Hawking radiation, and starts to evaporate away and disappear with a pop. I'm calling it a pop because by comparison with the amount of energy in this thing, a pop is only like an artillery shell going on in this room. Will probably kill everybody here, but cosmologically, it's a trivial little thing. Okay, so that's what happens to the black holes. They'll disappear. So we need that. But that's... Anyway, so the main thing that will be running around in the remote future will be photons. Of course, it's the main thing, and there will be some other things running around. There'll be some electrons. Some of them will annihilate positively charged particles and so on, things like that. But they will last to infinity. Some of them will meet a positron and go poof, and just produce photons. But on the whole, a lot of those will still be running around even with black holes. And I worried about that a bit, although by far the most will be photons. To make this work properly, you should get rid of mass. So I have a proposal. It's not observed, but it's not inconsistent. In fact, it's fairly consistent with the idea we have a cosmological constant, that mass sort of fades out in the remote future. I'm not saying that charged particles disappear by decaying. The mass of them ultimately fades away, so that asymptotically there will be no mass left. That's not part of conventional particle physics, but it's not outrageous. There is nothing in what we understand about particle physics that contradicts that. In fact, you might think the cosmological constant is fairly consistent with such an idea. What about the Big Bang? Now, that's another story altogether, because I said that's something very special. Now, why do I need something very special? Well, there's a story, which I'm going to tell you, which is a sort of obvious story in a way, but can't quite see why cosmologists don't worry about it so much. I regard it as the mammoth in the room, why they don't seem to worry about this huge problem. What's this? Well, why do we believe in the Big Bang anyway? One of the best reasons has to do with this cosmic microwave background. This is radiation coming in from all directions, electromagnetic, in other words, photons coming in all directions, very cold. It's about 3 degrees absolute, so it's very cold. But nevertheless, it has a thermal spectrum. That is to say, we have a frequency. It's made of different frequencies. And if you plot the intensity up this way and the frequency this way, you find that it fits very closely to this curve, which is the famous Max Planck curve, which was sort of the origin of quantum mechanics. And these lines, these vertical lines, are the error bars, where you have to bear in mind that the error bars are magnified by a factor of 500, so even the worst one here is really hugging the incline, so you wouldn't even see anything deviation from the incline in the picture. So the Planck curve is very, very closely approximated by the actual radiation. And what does the Planck curve tell you? What's it tell you you're looking at? It's tell you you're looking at sort of, well, thermal equilibrium. You're looking at a state of maximum entropy. Now, I want to say something about entropy, because the second law of thermodynamics tells us that the entropy, which is a sort of measure of randomness, let's get away with that, a measure of randomness which is increasing as time goes on. So that gets more and more and more. It's an observational fact, and it's also regarded as an absolutely fundamental foundation of physics. Now, let's say this in a different way. The entropy increases into the future. Another way of saying exactly the same thing is if you go into the past, the entropy decreases. So as you go down and down and down and down until you get to the Big Bang or close to it, and you see the entropy is at a maximum. Now, you don't have to be a really outstanding mathematician to say there's something a little puzzling. You go down and down and down and down until you reach a maximum. It's not quite the right way around. So it looks like a paradox. It's not really a paradox, because what you're looking at here is the result of matter and radiation. And it's all completely randomized, the matter and radiation. What you see is the radiation from it, and that gives you this Planck curve. So yes, the matter and radiation we're at some sort of maximum entropy state. But there's something else which you don't see in this curve, which is gravitation. Now, gravitation is in a very peculiar special state. And you can understand the second law of thermodynamics if you say that the entropy in gravity was set at very low or zero at the beginning, and the entropy of everything else was extremely high, which is a huge imbalance. And the mammoth in the room is this thing imbalanced, staring you in the face, and somehow people don't say, oh, there's a problem there, is there? I mean, usually you see a list of what are the major problems of cosmology, and they say dark matter or dark energy or dark web or whatever it happens to be, or something to do with densities and cosmologies and factors like that. Nowhere is it mentioned this puzzle, that in the very early universe, you have this extraordinary imbalance. And how extraordinary it actually is, I'll come to in a minute. But before saying that, let me describe the nature of this imbalance. You see, low entropy in gravity means basically a uniform state. So high entropy would be a non-uniform state. I'm going to have trouble finding the slide I had last time. For some reason, even with my new system here, I've gone and lost it. If you bear with, oh, it's right here. Here we go. Now, you see, a smooth state in gravity is a sort of low entropy state. You can imagine the universe initially had material uniformly distributed, which I should say is also something which we sort of observe in the cosmic microwave background, because if you look around in different directions, you have to correct for the Earth's motion. It's an amazing thing that the Earth, you can see it, how fast it's moving through this background radiation. If you correct for that, you see in the sky a temperature variation which is of the order of about 1 part in 10 to the power 5. So that's pretty uniform. So the universe is very uniform, which is telling us that, well, it's very uniform, and as time goes on, it's not utterly uniform, but it's very uniform, and it will start to condense in various places, and you get galaxies, you get stars, and these stars will be bright spots in a dark background, and this is where life on Earth gets its low entropy from, because you see the bright spot in the sky and the dark sky, and you can make use of that to, if the sky was totally uniformly hot, it wouldn't be any use at all. But it's the difference between the two, which is the low entropy that is made use of by life, for example. And the interesting second law that we have comes about because there is this imbalance, and the imbalance is manifested on the Earth by the fact that the sun, well, it's the main thing, is that the sun is a bright spot in the dark sky. So that comes about through the gravitational clumping. Of course, other parts of physics too, but the fact that the sun's there at all is due to this clumping. So clumpy state is the high entropy state. Now let's imagine a universe. You see, this is our universe, which gets more and more, a little bit more ununiform as the gravitational entropy starts to increase as you go into the future. But let's think of a collapsing universe. There we are, go the other way up. And I'm going to put some regularities in it, and I'm going to suppose that the second law of thermodynamics applies just as well. Those irregularities will start to condense into black holes and things, and these black holes will run into each other. They're closer and closer. These collapses between these black holes will increase, and there will be one unholy mess at the end. So that is what one would expect for a high entropy gravitational state. That's the generic situation. We don't see that. We don't see anything like that. The universe we find is that, not this. Now, that would be much more likely. In fact, you can estimate how much more likely. I talked about the paper being 125 to 1, the effect being actually there. What about this? Well, you have to think of probabilities like this. The chance of that happening by chance would be something like 1 part in 10 to the power 124. Now that's absolutely ridiculously stupendous. So it's a real question. Why was it like that and not like this? And I should say inflation doesn't do any good at all. It can't get even started in this picture. You need something almost like this even for inflation to consider working at all. It doesn't do anything to that kind of model. So the fact that it's like this and not like this is key to what I want to say. And why it's not like this, why it's not like this and is like this, is, I regard, as one of the major things we have to understand in cosmology. And as far as I can tell, there's no other model besides the one I'm going to give you which does give you a sort of explanation for that. And inflation by itself certainly doesn't. Okay, what I'm saying is, in our universe, it is of this stretchable out to be uniform kind. I used to say something like the Weyl curvature hypothesis, which would mean explaining what the Weyl curvature is. I'll come back to it later anyway, but never mind. It's a measure of curvature, which is the gravitational measure of curvature, if you like. And you could postulate that that measure of curvature happens to be 0 here. But that's a bit hard to work with, and it's a bit hard to say what you mean by it in a clear way. And my colleague Paul Todd in Oxford has a much better way of saying it, which is to say, you can do this stretch. So that doing this stretch gives you a huge constraint on the Weyl curvature, and this is the hypothesis that we make in a conformal cyclic cosmology, that this stretch is such that you could continue the space-time in a nice conformal way into the past. Now, Paul wasn't saying you actually do that. He was saying that this is a mathematical statement of how special it is. Now, I'm saying you can go into the future, that photons come and run into this boundary and they don't notice a thing. That's the idea. And photons could be coming from somewhere else prior to this. So that is the idea. And if the remote future can be conformally the Big Bang of the next eon, it has to, if this is a smooth join, then it has to satisfy something like Paul Todd's condition, in fact slightly stronger, which I'll come to in a minute, and that is what I'm postulating. So the idea is that the postulate is we have this infinite series of conformally connected eons, and this does require a Big Bang of this very particular kind that we actually seem to see. Okay. Now, there are various questions that need to be addressed here. One of these is how on earth, very reasonable question, how on earth can the second law of thermodynamics hold in a cyclic universe like this? I mean, the entropy should surely be going up and 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 up, and that is not going to be consistent with this sort of picture. Well, I worried about this for quite a long time, thinking all sorts of wrong things first, and I'm going to tell you what I think is the right explanation, which has to do, well, with the following. First of all, I should make the point that in our current universe, as we know it, when I say current state of the universe, if you like, the entropy in our universe is almost entirely, by far, the majority is in black holes. Supermassive black holes, far more than anything else. It utterly dominates the entropy of the universe. Now, that's the first comment. Second comment is, as I just showed you, these black holes, after you wait long enough, they evaporate away by Hawking evaporation. Now, the question is, what happens? Now you have to call Hawking to your assistance, or the other way around. Depends which Hawking. You see, the original point that Hawking made was in this study of black hole evaporation, very important and influential work, was that information is lost in black holes. Or if you put it another way, degrees of freedom are lost in black holes. Now, I think he was right the first time. However, in later years, he's changed his mind. I think he was badly influenced by his friends. I shouldn't say that, should I? But his view was somehow the information has to come back again. And that, I should say, is a common view amongst physicists. And the reason they say that is because if information is lost, this violates a fundamental principle of quantum mechanics, which is what's called unitarity, and therefore, no, we don't want to violate that. Now, my view is that unitarity has to be violated. I'm not going to tell you exactly what unitarity is, but let me sort of tell you. You see, in quantum mechanics, you have two procedures. One of these is the evolution of the quantum state, which is governed by Schrödinger's equation, or that's what's called unitarity. There is a deterministic evolution of the system into the future, which is the unitary evolution of the quantum state. However, this does not explain what we see. I mean, Schrödinger introduced his famous cat as an example to show the absurdity of his own equation, because his own equation tells you that if you follow it, you could quite easily produce a cat that was alive and dead at the same time. And sometimes people say, well, this is in a box, and you open the box, and somebody looking at it makes it alive or dead. Well, that, I'm not sure what Schrödinger's view was. I think his view was there's something fishy going on, or catty or whatever it is, going on here, which he didn't really believe that we understood properly. There's something in quantum mechanics we don't really understand. I agree with him. I agree with Einstein, who said more or less the same. I agree with de Broglie, who certainly said something like that. Most surprisingly, perhaps, I agree with Dirac, who was the great physicist who perhaps first put quantum mechanics in a form which everybody uses now. And if you read carefully what he allowed himself to say in later life, you see he really thought, yes, there's something fishy going on. We need a replacement for current quantum mechanics, and something is not quite right. Now, the thing is that when you evolve the Schrödinger equation, you get, for example, with you might have a particle which is decaying, and maybe the decay enters this detector, and this detector maybe goes ping when it sees the particle. Well, the ping is something you hear. It's supposed to be a classical thing. The particle was a quantum thing. How did it get converted, get measured in a certain sense by this device? Well, there's no explanation. Because if that device is another quantum thing, as it should be really, if you say everything's quantum, then it won't go ping. It'll be superposition of ping and not ping. And what do you hear? Superposition, well, it doesn't make any sense. It doesn't correspond to the world we perceive. Now, there are all sorts of views about this, as you might expect. My view is that, along with these great physicists I mentioned, I know you shouldn't appeal to authority with these arguments, but my view is that there is something ultimately wrong with quantum mechanics. And what is wrong with quantum mechanics has to do with gravity. And there are reasons one can say that's plausible. So what I'm going to say is that when the measurement takes place, it's due to the fact that certain mass displacements take place in your device, and they're sufficient to change the structure of quantum mechanics from this superposition of different alternatives to one or the other, however many there are. Now, that will come in later in my talk, so I have to stress that point. But this is not unitary. What happens in a measurement is not unitary. So I'm saying it's a gravitational thing, and therefore I'm saying with black holes, which are really very gravitational things, unitarity is not going to hold, and so it's perfectly all right for black holes to lose information. In fact, it's perfectly all wrong for them not to lose information, because you can see there's a great problem with that if you draw appropriate diagrams and you see the problem with it. Anyway, so that is my view. I forget what I've actually said on this slide, but that is more or less what I'm saying. Okay, that will come in again in something else. Now, I should also make a remark about what the paper I said at the beginning. I'm not going to talk about this in any detail, but there was a prediction that I made some time ago when I put this theory forward, that I'm worried about how on earth could you see whether it's right or not, or be one of these things which forever you'll never know the answer. And I thought, well, what's the most violent thing I can think of which has a chance of being a signal that could get through from one eon to the next? Well, what's the most violent thing I could think of after the Big Bang itself is the encounter between black holes. We know from LIGO that black holes are something like 30 solar masses or so produce a signal that can be seen I forget how far off away from these things in distant galaxies, can be seen by suitable detectors. But this is something on a huger scale than that. We're looking at black holes running into each other and producing a gravitational. Well, you see, this is the eon prior to ours. This is our eon. And I have some black hole world lines here, and then they run into each other. This is a little bit more complicated. We have several of them. But you see these rings coming out here, which will be the effect of the gravitational waves coming from the collision here. And through a little bit complicated, which I'll say a little bit about later, this will convert itself at the crossover into signals which we can actually see. And the claim is that this Polish group actually did see this, and they certainly see something. It would look like rings, a little bit hard to detect, but nevertheless, where the temperature is slightly higher or slightly lower than average, and is slightly more uniform around the ring than elsewhere. I don't want to say much more about that, except that that is the main observational test that has been used so far to test this scheme, and it does seem to indicate that there may well be a signal of that sort. I want to say a little bit more about the mathematics of the scheme, so I'll get a little bit more technical here. First of all, there's something very curious about the Weyl curvature. I said I wouldn't say much about the Weyl curvature, but I'll have to say that now. It is the conformal curvature. It's the curvature of the space-time which is independent of the scaling. So it's the structure of a space-time which is there even when you have this conformal rescaling allowed. And it's usually written by a thing called the Weyl tensor, which I represent by C, that's the conformal tensor. Now, when you rescale your metric, and I use this capital omega thing to go from one scale to another, the Weyl curvature scales in this way. But I noticed a long time ago a very curious thing, that if you're interested in wave propagation, then the thing that you're really interested in looks like the Weyl curvature. It's the same thing, but when you change to another scaling for the metric, it scales differently. And that's the thing I'm calling K. So C and K scale differently, even though with a particular scaling that you have originally from Einstein's theory, the K and the C scale differently. But it's the K that tells you how gravitational waves propagate, and that remains finite, but because of the way these conformal factors work, the C must be 0. So the Weyl curvature is 0 at the beginning of the next eon, since it's got to match as you go from one to the next. It is 0, and so therefore this proposition that I was promoting, that the Weyl curvature should be 0 at the Big Bang, Paul Todd's criterion does indeed, in this context, give you 0. So that fits, and that works all very well. I think I'm going to say these things again later, but yes, the thing is that, let me say this later, but let me make a comment initially. You see, you might say, how do these signals get across if the Weyl curvature is 0 at crossover? You have to look carefully at equations. And those equations tell you that even though the Weyl curvature is 0, its normal derivative is not 0, and you have to ask, what does it go into? And this requires looking a little bit more at the equations, and here's where I think just waffle about the equations while I show you these pictures, so you don't have to worry too much about following them. See, what you do, here is the pre-crossover universe, and here's the post-crossover. So this is the remote future of the previous one. This is the Big Bang of the next one. And these different G's with circumflexes and Hutchexes are for these two different parts. And you have these conformal factors. And I have an important hypothesis here, is how do you flip over from one to the other? And that is this big omega goes into a little omega by changing into its inverse. The big omega goes to infinity at the boundary. The little omega goes to 0 at the boundary. Now, the big omega, initially, isn't really there. It's just a way of writing your equations. It's only introduced so that you can make Einstein's equations hold right up to the edge. You see, Einstein's equations wouldn't make sense at infinity, but you can make them make sense by introducing this factor as a sort of pseudo field. Well, I'm going to call it a phantom field. I think the word phantom is sometimes used in a different context, but let me call it a phantom field. It's not really there. It has no degrees of freedom. It's just put in to make Einstein's equations allow you to talk about them up to the boundary. It makes everything conformally invariant. It's not really a physical field, but it does have an energy momentum tensor, which is this funny expression here. And you do have the equations of Einstein pre-crossover, which is that the energy momentum of matter is equal to the energy momentum of this funny phantom field. Okay, that's just a way of writing things. But when you go to the other side, because of this reciprocal hypothesis that big omega goes to the inverse, minus the inverse actually, of the little omega, that suddenly means that this capital omega becomes an actual field. And it's a field which picks up the degrees of freedom of gravity and only gravity. It's actually the fourth derivative of this field it comes from the Weyl curvature previously. And it's a scalar field. It doesn't have any indices on it, so it's a scalar field. It doesn't have any directional qualities. So what is it? See, when you change to the other conformal factor, the way the mathematics works is it now becomes a real field. It has to be a real field which dominates everything else. Physically, you can think of it as, well, you've got the stretched out universe. You've got to have something to pull it back again. And what pulls it back, in a sense, is this new field. Now, what right do I have to introduce a new field in physics which dominates everything else? I don't, because it's already been done. There is this dark matter, which seems to be out there, which dominates the material of the universe. It's by far the majority of the material substance in the universe. It's called dark matter. Nobody really knows what it is. It's the major part of the mass of a galaxy, and it's first observed because of the stars going around. They go around too fast in order to compensate for the extra attraction of this dark matter, and that's how it was first observed. And all sorts of observations, cosmological, tell you it's there. Now, if it's there, and if it's really gravity, because it's picked up on the gravitational degrees of freedom, there's nothing else in physics going on with regard to it. It tells you something about what it ought to be. Now, one thing it ought to be, and I think I've listed these things here if you can read them. One thing it ought to be, what's its mass? Well, the only thing it can be, if you've just got gravity, roughly speaking, is a thing called the Planck mass. Well, it might be 8 pi times it or something like that. But it's something of the order of the Planck mass. How big is the Planck mass? It's about 10 to the minus 5 grams. That's about the mass of the eye of a flea, I believe I got from Google or something. Now, that is huge if you're talking about particle physics. Now, it's not necessarily huge if you're talking about, well, dust particles even, it's huge. I asked Jim Peebles and I asked Joseph Silk, is it reasonable from the point of view astrophysical observations to have something, I mean, what are the range of sizes? Well, Peebles told me, well, it's absolutely huge. They could be tiny little things less than an electron, or they could be individually of the mass of the sun. I didn't believe that, but they could be. There's nothing apparently against the observations of astrophysics. So what about Planck mass? Fine, way just suitable. And Joseph Silk seemed very happy with that. So I'm saying that is very plausible from the observational point of view. It's practically necessary from CCC point of view. You've got to have this field there, otherwise the equations don't work. And if it's a proper field of particles, and if it's just gravity, it's got to have something like the Planck mass. It's got to interact only gravitationally, which is what dark matter apparently does. It doesn't seem to interact any other way with other matter apart from gravitating. That would be consistent with this scheme. So I'm saying that's what it is. Now, is it a stable particle or what? Well, you see, I don't like the idea of it being a stable particle, because each time you go to crossover, it produces a whole lot more stuff, and you produce more and more and more, and the universe would be even more crowded with it than it is, maybe completely, utterly. So that can't work. So what I'm saying is that it decays over the history of the eon and disappears finally at infinity. So there is a rate of decay. Now, you can sort of estimate what that rate of decay should be. I haven't got a terribly good estimate. I should say that there are two numbers which come into gravitational physics. One is the gravitational constant, and that gives you the Planck mass scale. The other thing is the cosmological constant. That gives you a completely different scale. Now, the Planck mass scale would determine the mass of this particle, and the decay rate would be determined by the cosmological constant. So this particle will have a half-life, like anything radioactive, but that half-life will be something like, maybe even more, something like 10 to the 11 years. So that's even longer than the length of time from the Big Bang to us in standard cosmology. Not hugely more, if you like, but that's the sort of thing. So that means even though in an individual dark matter particle won't decay, you sit there waiting for it to decay and you won't see it in your lifetime, but since the universe is so full of these things, their decays will be happening quite significantly over the universe. Now, is there a possibility that you might see them? Well, you see here I have a slide which says a bit more about dark matter. I think I should just talk, and if you read what it says on here, it might illuminate what I say, especially the things I forget to say. That'll be probably on there. Okay, so it's basically, from the point of view of particle physics, a stable particle. People often worry about, shouldn't it decay in 10 to the minus 40 seconds or something? Well, no, it's a stable particle. But it's not quite stable because the physics you should be talking about is with the cosmological constant. And so then it's allowed to decay. So it will decay. In what into? Well, it's only interested in gravity. It's not interested in anything else. It doesn't interact with anything else. So the only thing it can decay into is gravitons. That's the particles of gravity. Well, I was having this discussion with Yvette Fuentes, who one of her interests is making gravitational detectors, and I wondered, could you detect gravitons from this decay? And then in this discussion, it became completely obvious that you better not, because a graviton has an energy of the, well, mass energy of a flea's eye turned completely into energy, and that's this artillery shell which you wouldn't like going off in this room. So if you had a gravitational wave detector and you actually detected this graviton, it would blow the thing to pieces. So it's not very good news. I mean, perhaps that's not a good physical argument, because maybe that's happened and nobody's got a gravitational detector sensitive enough to see it. But I didn't like the idea very much, so I thought again. And I thought this particle, I'm going to give it a name here. I'm calling it an erebon. I'm calling it an erebon because, well, I looked up originally to see if there was a Greek god called anything. And at that time, I looked up on Google and Wikipedia, I guess it was, and it didn't. It said there wasn't a Greek god of darkness, but there was an Egyptian one, and he was called Erebos. So I thought, that's fine. I'll call these things erebons. And then I looked up in Google again several months later. It says, yes, there's a Greek god called Erebos. So I don't know quite. You have to be careful with these things. Anyway, the current view, and I checked up now a little bit more carefully, that there was a Greek, I don't know whether it was a god or a demigod or whatever he was, but he's fine by me because he was he was primordial. He was right there at the beginning and fine, just right. So erebons are what I'm calling these particles, and they, anyway, let me move my slide to the next one. They don't interact with anything else except gravitationally, and they have this very long lifetime. Maybe one can see them with gravitational detectors. But the point I want to make here is that if my ideas about quantum mechanics and general relativity are right, these Planck mass particles won't stay very quantum mechanical, because as their wave function starts to spread, it will immediately collapse, because they are so massive that the criterion that I'm proposing for the collapse of the wave function, which I'm supposing for completely other reasons takes place, that will make these erebons completely collapse to be localized. They will behave like classical particles. So if they're classical particles, then they will decay into gravitational waves. Now they will therefore be a classical gravitational wave. Now let me say, I'm not quite sure that I've got the right order of these things. That's probably telling you, no, that's, yes. Let me go to this slide here. What do they look like? Well, you see, they're gravitational waves, but they're probably very, very high frequency, because this frequency of 10 to the minus, 40 hertz, 10 to the 40 hertz, obviously ridiculously huge. So the frequency is very, very high. But would you see them as high-frequency gravitational waves? Well, this is a bit of thing that I did a long time ago, looking at gravitational. You see, you can think of gravitational waves in terms of lenses. Take an optical bench, and you can put lenses like that and see what they do. And if you have two positively focusing lenses, put them right up to each other, the power of the total is equal to the sum of the powers. Power is the reciprocal of the focal length. And if you put them next to each other, then the power of the two together is the sum of individual powers. But if you pull them apart, there's a correction term due to the separation. Now this will apply also if you take astigmatic lenses. So imagine the one which is as much focusing in this direction as that direction. So through a right angle, one is positive, that's negative. And that's like a gravitational wave. It squashes in one way and stretches out the other way. And that's exactly the effect that a gravitational wave would do. But if it's highly oscillating, you have to think of these astigmatic lenses, put one right against the other one, they cancel out, pull them apart. The correction term will be a positive focusing. And that's like the energy carried by these gravitational waves. In fact, you get the energy that way. It's a way of doing it. So that if it's oscillating between these two, then very highly oscillating, well, it will look like a pulse of energy, not of gravity. It's interesting, you see. If you ask me whether LIGO would see it, imagine the two arms that LIGO has. These are several kilometers. Well, I forget what the number is each way, like that. And if one gets squashed and the other stretches, you see a signal if it's coming in against it. But if it's one of these things coming orthogonally, they both get squashed at once, and you wouldn't see it. But if it comes in along one of the arms, then the other one gets squashed, and yes, you would see it. So it's possible it's seen using things like LIGO. So I wondered about this. I was giving a talk in Vienna, and at the end I think I said, well, maybe LIGO people are seeing it, but since it's not the kind of wave they're looking for, they've thrown it in the rubbish bin. And then I think it was later the same day or the next day that I was told that there was a lot of argument going on between some physicists in Copenhagen, headed, I think Andrew Jackson was the one I know, and several people in Copenhagen who'd claimed to see, along with the LIGO signal, if you look at what they refer to as the noise, you see there are two detectors, and these two detectors separated by, I forget how many thousands of miles, but one of them sees the effect before the other one, and this gives you some idea of the angle at which the thing is coming from, because you know the speed of light from one to the other, and the gravitational wave should be going with the speed of light, so it tells you what angle it's coming in at you. Now, what the Copenhagen people did was to look at the noise surrounding the signal that they had available from LIGO, and they found at the same time lag from as the gravitational signal, the noise was also significantly correlated. So they wrote some article about this, and they've got all sorts of trouble with the arguments going backwards and forwards. And so I thought about this, and I started worrying. I said, oh, well, the gravitational signal from the black hole encounters has nothing to do with them, but what it might be is the erebons coming from the galaxy in which they sit. Can you see a signal? And then I didn't actually do this enough, but I worked out some figures later, which is important. I'll come to that very shortly. I'm sure I'm running out of time. But all I want to say is that maybe these guys are seeing a signal which is not what the LIGO people are looking for, but maybe it's there. I'm not sure about that at all. It could be or it might not be. It depends on certain details. So let me say a little bit about this, and I can't remember what I have on this slide now. But anyway, the idea is that you would, if you're going to see the erebon signals, well, you might see individual ones as erebons in our galaxy go off, bang, 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 and maybe ones close enough to be within our solar system, possibly with detectors of the sensitivity that LIGO has, might see them. I'm not sure the details of that. But the other thing is you might see from a distant galaxy where the numbers of these erebons is absolutely huge. And then if you have a signal which is discernible, you might see an effect. Now, you're not going to see an effect if it's just uniform whoosh from something, you know, if it's just a random signal coming to you. How do you know the galaxy is there rather than somewhere else? I mean, if you shift it by a certain fraction of a second, it's going to look just the same. But then I had the idea that maybe it has some structure to it. And actually, in an email, I mentioned, this was of somebody called Sabine Hossenfelder, who writes blog on these things and sometimes irritates people by complaining about their theories. And so she was complaining about mine a little bit. And so I was trying to say, no, maybe you can see a signal from a distant galaxy because there's some structure. And she said, oh, you mean HBT. So I wrote about HBT, what's that? And so she said, oh, Hanbury-Brown twist. Oh, Hanbury-Brown twist. Ah. Now you see, I said these erebons are like classical particles, but that wouldn't be entirely true because they would really be quantum particles, but all the time localizing themselves. But they remain what are called bosons. Now, photons are examples of bosons, and the Hanbury-Brown twist effect is something where you see an effect due to photons coming from distant parts of a star. They can estimate the size of a star by looking at effects which come about through the fact that these are not independent of each other, that the individual photons are entangled with others simply by virtue of the fact that they're bosons. Now, if erebons are bosons, something similar is very possibly happening. And so you will see a clumpiness, like the Hanbury-Brown twist thing, which would be from the huge number of erebons decaying from a galaxy. The signal will not be just some whoosh, but some random signal which is with a structure to it. And so maybe, and I'm only saying maybe, you can see these with gravitational wave detectors. Now, I don't know the answer to that. I don't really understand the HBT well enough to be able to give a good prediction. The final thing I want to say, well, I guess I've got 2 slides. I've probably run out of time, have I? But since people are still here, they haven't all walked out yet. Let me just quickly say 2 things. You see, the erebons play 2 roles in CCC, 2 quite different roles. One of them, going back to inflation, this is the role played. See, this is meant to be the crossover surface. I hope you can see this. This is the crossover surface R1 from our previous eon to us, and this is the Big Bang of the previous eon. Now, there will be erebons here decaying, and they will produce a signal here that we might see. Now, one of the reasons inflation is so popular with physicists is it's the only thing they can think of which explains what's called the scale invariance of the cosmic microwave temperature variations. So you look over the sky and you see the temperature varies as in different places, but it has a structure of variation which, if you change the scale on the sky, you see the same pattern at different scales. And the only thing that people could think which produced this was an exponential phase in the early universe, where the universe was self-similar, and this produced this scale invariance in the signal. But in CCC, there's no inflation. It would wreck the connections between one eon and the next. It just doesn't work in the scheme. However, there's something like it in the theory, because the exponential expansion, self-similar expansion of the previous eon looks a bit like inflation in our eon. And so that exponential expansion, if there is some production of particles or signals of some sort, that could produce the effect that the scale invariant signals that people see are. So I'm saying it's not inflation, it's erebon decay. And so that's an important role that is needed for erebon decay. I need to look at it all over again, because the Hanbury-Brown twist effect will work here too, and so it's got complicated. And so I don't know the answer to whether you get the right answer here or not. But you certainly is a possible cause of these scale invariant fluctuations. The other thing, I think this is the picture I should be looking at there, that's right. This is the crossover from previous eon to ours. These are the erebon decays, and the question is, do they give you something self-similar? The other thing is erebons. I'm not sure. You might see erebons in this is us now in here, and then you might see the erebons here. So those are the 2 ways you might detect them, and they connect to each other, and figures that you get for one will relate to the other. And so that needs more work and understanding, and this is my primitive little job of trying to work out numbers. I'm not going to say too much about it, because I think I need to think about them all over again because of the Hanbury-Brown twist thing. But I was trying to work out how many erebons per second are emitted by a galaxy, and I think the number is 10 to the 38 or something. Anyway, if you want to get some idea of figures, it's here. But I think I even need to think about these figures again, because I haven't taken into account Hanbury-Brown twist, and that would be very relevant to erebons from distant galaxies, and whether they would be detectable, maybe with detectors a little bit different from the ones that are LIGO and other detectors, but I don't know. Anyway, let me leave you with that. It's an exciting subject because of this, also because of something else which I'm not allowed to tell you, because there are some other signals which seem to be out there, and do seem to be something that CCC has an explanation for, and seem to have a very strong signal. But my colleagues won't allow me to tell you, so I won't tell you. But maybe next time. Thank you very much.
Thank you for that really